Good morning. Welcome to lecture 42. Today is June 12, 2023. Please note there are two errors. There are lecture numbers about numbering of lecture. There were two errors in the last two classes. Correct is follow. June 8, 2023. The lectures were two lectures. That should be lectures 38 and 39. And June 9 means last class. June 9, 2023 is lectures number 40 and 41. And today, the next lecture 42. And today date is June 12, 2023. Please note this correction and then we proceed. Before we proceed further, this, please note this, actually since you are actually interested in this entropy and all this, I am giving you another handout and it will not bad, not good, not difficult. So, this is another, so this I will give, okay. Further reading materials from this time key what? K Dendic. The principle of chemical equilibrium. The principles, this is the book name, the principles of chemical equilibrium. Fourth edition. Okay. So reading material, topic. Okay. Apparent topic is actually from the topic is okay. Subject is okay, topic. A statistical interpretation of entropy. Page number अच्छा topic topic is okay. Topic, right? Related to the statistical interpretation of entropy. Page number 48 to page number what? Sure. Topics are exact. Topics are section 1.17 natural processes or mixing processes. Natural processes as mixing processes. Mixed termness, so mixing processes. Page 48. Okay. Section 1.18 molecular interpretation of the second law. The molecular interpretation of the second law. That's it. We take this. get this Xerox for yourself, okay, what is copy it, and return me this one, okay. Then you have to take help of them, okay, get and circulate, okay. Remember this thing that this for your study later, not this is nothing to your, okay, this test, class test or semester, no, okay, whatever I discuss, okay. Reading materials for additional your, okay, additional study, for your additional knowledge, reinforcing your knowledge and other, okay, covering other materials. But this is actually not for your, okay, your class test or semester examination. So don't expect, and I will not actually ask anything from there. Whatever I asked in the class myself, this is actually yours. This you should consider this. That you consider, but this you have to of course read to have your fuller knowledge of, okay, entropy, second law, and entropy, and entropy as, okay, statistical interpretation. All these things are given. So Gaskell book one reference, and Denbigh's book another reference. So in case okay, this time, this semester, this time, or later in your life, later in your life may be helpful. So that's why I am giving you all the reading materials, all the source material for your knowledge. So this is your, remember this. Next, today's this discussion is assignment number 4. Okay, assignment number 4. Okay, what is the problem? Oh, this takes time. Okay, so can I remove this? You have taken down this. So assignment number 4. Okay, continued. What problem we discuss? Problem 4 and 5 today. These are very important problem. As I remove this. Problem 4. What is the problem? Let us write down. At a pressure of 1 atmosphere. At a pressure of 1 atmosphere, the melting temperature of lead is 600 Kelvin, and its latent heat of fusion is how much? 4810 at this temperature. Temperature is 4810 joule per mole. I am removing this part also. Joule per mole. Okay. If 1 mole of supercooled liquid lead, if 1 mole of supercooled liquid lead spontaneously freezes at 5 and 1 atmospheric pressure, calculate the entropy produced. That is delta S inverse. Okay. So where shall I write? Okay. Start solution. Okay, first of all, I tell you what, try to understand the given So many things. Giving Cp liquid lead liquid 32.4 minus 3.1 times 10 to the power minus 3 T. Again T joule per Kelvin molar, and Cp lead solid is 23.6 plus 9.75 times 10 to the power minus 3 T joule per Kelvin mole. The data. So this is actually solution. Okay? Solution. Why shall I write? Okay? I have to remove this. Remove this. No way. No way. No way. Solution. Start here. See, follow one thing. What is the melting point? 600. So, but 10 degree supercooling is done. So that it spontaneously freezes. This is called supercooling. Is actually very common. So you argue, sir, just below 600 it will freeze. Why, sir, 10 degree or for that matter 20 degree? No, supercooling is required. This is very important issue and common. We often supercool. Why? Because there is nucleation barrier. To overcome the nucleation barrier. So pure liquid, fast solid will be nucleus, and that has a big surface area is to volume ratio. The smaller the size, surface area becomes predominant relative to volume. Big size, no, surface area is relatively less than the volume. Volume is bulk. So when it happens, so then there is a nucleus. This you should study in physical metallurgy, another subject. But I am giving you the thing that supercooling is required to overcome the nucleation barrier. They call activation energy for nucleus. Nucleus formation. Or say, they also say that critical size should be overcome, and critical size decreases as supercooling is more and more. So more easier and easier becomes. So critical size. So these are the things. So that's why. So supercooling solution. Note, supercooling is required of a liquid metal for its freezing, solidification is required to overcome the nucleation barrier. No, right, I am repeating this. See, below this, just any temperature below 599 should be thermodynamically. Anything below melting point. For example, water 0 degree centigrade, below 0 degree, -1, it should be ice. But it doesn't form ice. The clean beaker water you take, put it freeze -1 degree centigrade, there is no ice. Because it is clean. But again you see, if you put some ice already there, formed ice, already there, chunk of ice, already under water, then it will just below. -1 degree, it will be solid, whole water. Because that is actually, there is no barrier. Nucleation, there is a site, there is actually substrate there on which nucleation will take place, and there is no barrier. On that solid ice, new ice actually, the next, okay, well, the newly formed ice will be growing on that, no barrier. But when nothing is there, pure liquid, the first will be nucleus, and there are tremendous barriers because of the surface free energy and something you should learn later. So overcome these barriers. So that's why, in fact, you'll be surprised to hear that -20 degree centigrade is still water. You say -20 degree, below 0 degree, ice you say, ice. But this is the case. Okay, so careful about this. So that's why supercooling is rule rather than exception. This is not any surprising thing. It is always will be supercool. Given this. So what is happening here? So barrier. So if I sketch you the problem follow the problem. So just see this. Follow with me. Lead liquid. What temperature? 1 atmosphere. I'm not talking about 1 atmosphere. If you are interested, 1 atmosphere here. Open to 1 atmosphere. Open to 1 atmosphere. Open. Everything is open. Lead liquid. What temperature? 590 Kelvin. Why? Follow this. This is in a reservoir surrounding. The universe means system surrounding thermostat. What is this temperature? Surrounding temperature is what? In a reservoir. Okay? This is surrounding. Supervised place actually is and it's if one is super cool to this. This is the thermostat. Surrounding. What temperature? Tell me. 590 Kelvin. So liquid is given, and this is of course a non-equilibrium state. It goes to where? Tell me. Goes to where? Again draw. Sorry. Again draw here inside. Draw. Oh boy. So you have to keep this first. And this, and then you draw this container. So it will be again. It is subjected to 1 atmosphere is no problem. Open to atmosphere. No problem. Lead solid. It becomes, see below melting point, supercooling, freezes to lead solid. 1 mole. So write 1 mole, AC5, 1 mole, lead solid. What is the temperature? This is still standing, surrounding, thermostat can down. It is still, okay, thermostat, surrounding, okay, thermostat, and surrounding, it is still there, running 590 Kelvin. So what is the temperature here? 590 Kelvin. Follow this. State 1, state 2. This is what? Spontaneous process, like spontaneous process. Okay. What I said? What is state 2? What is this state? See, what is this? Liquid 590 Kelvin is not equilibrium because 590 Kelvin, liquid solid both exist, and below is should be solid, but 590 Kelvin liquid is supercooled, suddenly exposed to 590. At that moment, it is non-equilibrium, no surprise, non-equilibrium. This is running into the equilibrium state. This is equilibrium. Solid can be below melting point. So this is the equilibrium state. What is the spontaneous process or definition? If system moves from initially spontaneous non-equilibrium to equilibrium, makes sense. Spontaneously it is somewhere spontaneously underway. So no surprise. You know the answer. You know it should be. What is the answer? Delta's universe should be. What answer? Positive. Good. Greater than 0. So let us see what happens. So what step by step? So start. So first you find delta system. You follow this, you just follow this. Let me know, 5 minutes I'll be there. 5 minutes before. Delta system, okay. You follow this quickly. System, right, delta system, calculate. Achha, system moves from state 1 to state 2, that is, okay. Achha. 1 mole lead liquid, right in language, lead liquid, right. 590 Kelvin, 1 atmosphere. This I am writing, state 1. 2 goes to, right. What is this? State 1. To 1 mole lead solid. 1 mole lead solid. What temperature? Tell me. 590 Kelvin. The overall process, delta system, the overall process. Give me the sketch. Okay, this is now break up. You break conveniently. Break up quickly. Let liquid break up. Break up quickly. Acha. Acha, I'm breaking up this. I'll give another picture. But let me another figure. But follow the breakup. You know, can you tell me? See, liquid, lead solid, easy breakup. What I said? It take to first 600 Kelvin freezing, and solid becomes solid, solid becomes again cool to 590. So let us follow this. Break up 1 mole. You write step 1 to 8. I'll tell you. Step 1 to 8. I will show the sketch later. Step 1 to 8. That will help you. Another. Quick. 1 mole. Quickly. Lead liquid. Tell me. 590. I mean, I'm not giving the 1 atmosphere is common. So goes to what? 1 mole. Lead liquid 600 Kelvin. Follow this. 600 Kelvin. Then second step. I'll give this. What is A to B? A to B. Quickly and very quickly. 1 mole lead liquid. This is the freezing point. This is the freezing point. Now make it at that. Actually, this is a reversible process. Is 1 mole. Don't worry about that. Lead solid. What temperature? 600 Kelvin. Third is what? Step B to 2. Right here. This is state 1. Right here once more. State 1. You write this. This is 1 atmosphere. This all. It clashes with the problem. This is already over. Remove this. This noting is removed. Remove this. 590 Kelvin 1 atmosphere. Right here. State 1. State 2. Right. State 1. State 2. Here also same thing I'm writing. Repeating. Another repetition coming. Step, what is this? B to 2. So you can see here 1 to A to B, B to 2 means 1 to 2. 1 to A, break up, 1, start, and this breakup will be convenient. Why I will explain. What is this? 1 mole, lead solid. Tell me, guess is what? Final is what? 590. Solid 590. It will be solid 590. Both are 590 finally. Liquid 590 cannot stay there. Should be solid to this. But to find the result, delta system, this breakup will be convenient. Always you do the breakup, okay? See, follow this. What is this? Okay, very good. So what is this? 1 mole, lead, what? Tell me, 590 back. This is the back. This is the actual universal problem. All metallurgists all over the world solve this problem. Okay? So this is the breakup. Now, can I remove this? This is redundant now. This is redundant. Now give the picture. I'm drawing this figure. What I have written here, follow this. Follow with me. Okay? And temperature, T. T is the temperature. Follow quickly. So, I'm drawing something. Follow. I'm drawing something. Yes, okay, very good. 1, state 1. This is my state 2. What is the temperature like this? Right, 590 Kelvin. What is this temperature? 600 Kelvin. Okay, what is this? 1 to A. Move 1 to A. What is this? A to B, B to 2. What is this, gentlemen? 1 mole. First you write this lead liquid, this write 1 mole lead solid. That's it. These I have shown. Follow this. Entropy of the system placed against temperature. These are the two temperatures. Okay, see what I am starting with. Follow. You draw this. What I have done? 1 to 2. 1 to 2. So draw this. 1 to 2. Alternative is directly 1 to 2, but this is difficult because data are not given there. Data are given for 600 Kelvin. Say, enthalpy of fusion for what temperature? At this temperature means at this 600 Kelvin. So 590 no data. So you can try this also. Thermodynamics always gives the same result if it is done correctly. All okay. Okay. 1 to A to B. What is this then? What is the state 1? 1 mole liquid. What temperature? 590 Kelvin. Okay. This is the state 1. And what is the state 2? 1 mole lead solid, right? Nicely. Lead solid. What temperature? State 2? 590. What have I written? 1 to 2. How I move? Journey, break up. 1 to 2, break up. 1 to A, convenient. A to B, B to 2. What is this? Tell me. What is this? 1 mole lead liquid. This is 1 mole lead liquid taken from 590 to 600 Kelvin. No surprise. Step 1 to A. A to B is what? This is the perfect phase transformation. Freezing. Okay, this is heating. This is the freezing. What is this? What is the freezing? 1 mole lead liquid, and this is 1 mole lead solid. 1 mole lead liquid at what temperature? 600 Kelvin to same temperature, freezing temperature same. 1 mole lead solid 600. The second step A to B, and third step is 1 mole. What is this? This 1 mole lead solid. 1 mole lead solid. Okay, coming from 600 Kelvin. Okay, is actually cooling from 600 Kelvin to 590 Kelvin. Say that's all set. Quickly determine. Okay, so you have to determine delta S1 to A, delta S A to B, delta S B to 2. Add them together, get delta S system. Then you take up delta S surrounding, together delta S inverse. This is the problem. So one by one. So first term. So quickly, let us write down this quickly. Let us not waste time. I don't have much time. Delta S now. Okay, now delta S A to B quickly. With me quickly. First, A to B is what? Delta S A to B. Oh, 1 to A first. Why A to B? 1 to step by step. 1 to A is what? Integration, tell me, guess. Temperature increase. Whatever it is, temperature increase what? ds is Cp dt. ds is constant pressure. This constant pressure I have not mentioned, 1 atmosphere. ds is, remember, ds is Cp dt by T. Constant pressure. Enthalpy, dH is Cp dt. Entropy, Cp dt by T. dq reversible by T. dq is n Cp dt. N is 1 here. Cp dt. dH and ds. dH is Cp dt, but entropy will get a. So quickly. So Cp lead liquid dt by T, temperature running 590 to 600. Quickly, you do yourself Cp liquid extract. One I am doing, but I don't have time. So 590 to 600. What is Cp liquid? Copy there. Copy from this. 32.4 minus 3.1 times 10 to the power minus 3 T dt by T. Happy? So how much it is? If you do this correctly, I'm giving you this time 32.4. You know what is integration dt by T is ln T. ln 600 by 590 plus what is this? Or rather minus, because there is a minus term. So minus 3.1 times 10 to the power minus 3. Tell me again. Okay, this is what? This is T is there. Remember, T is that dt cancel dt. dt integration dt is T2 minus T1. 600 minus 590. If you do yourself, this part I 0.54 minus 0.03 is 0.51. What unit? Joule per Kelvin. 1 mole is already given. So this is 0.4. You know, this is 0.4. 0.1 joule per Kelvin. 1. Step, what is this? Delta is 1 to A. So I am removing this part. No longer. Delta is B2. Next. Delta S, tell me. A to B, which is pure phase transformation at what temperature? The melting point. Normal, this is called normal melting point. 600. Normal melting point. Because this liquid will be solid only. So what is this? Quickly. Q reversible by T if you are interested. Write this, but this will be constant pressure. Reversible. Q is same. Okay, but you write what is this? Is what? Q reversible is what? Delta Hm is what? Melting. Name for melting. Latent diffusion means melting. So, but it should be melting or freezing. Tell me, freezing or melting? Tell me. What is this? T. What is this? T. What is the T? Melting or freezing. Okay, melting or freezing. Okay, freezing. Freezing means melting point. Actually, same. Is what? Minus. You understood? Melting is plus 480 liquid to solid to liquid. This much heat is needed. Back. Liquid to solid is minus delta Hm. So this is T freezing or say or melting, whichever you use. What is this value? Minus, write that 4810. But what is the temperature? 600. How much it is coming to? Minus 8.02. Write that nicely. Second is out. Third. Next. Still next. And delta is B2C and delta is B2C, B22. Then C, B22. Huh? 5 minutes. Cp, right. B2C, right. Cp lead solid. dt, right. What is this? This is coming 600 to 590. This you do same similarly. If you do yourself, you will get what? 66 B2C. If you do yourself similarly, do yourself. I am not giving this. I have don't have time. Okay, you do correctly. You do. Yes. Huh? dt by. Thank you. Good thing that you have noted this. That's great thing. There is B22, CP dt by 2. If you do this, okay, you write here. What you write? Integration once more. I am writing 600 to 590. What is the CP? Let's say copy. 23.6 copy and plus. Tell me plus 9.75 solid. It's solid. 9.75 times 10 to the minus 3t. What is this next? dt by t, as he said correctly, dt by t. So this is what? This will be what? If you do yourself, I'm giving you the result here. I'm not disturbing this one, okay? I may disturb also. I'm disturbed. First step I can disturb. Let me disturb this. What is this? Quickly. Is a minus 0.40 minus 0.09. How much it is? Tell me, is what? Minus 0.49 joule per Kelvin. Minus 0.49 joule. What about delta system is how much? Oh, sorry, I should have not removed this. This I thought. Okay. What is this? Delta S AB, A2B, delta S all. Can you start this? Start this point. Where is this? Delta S B22, A2B, B22. B22. Okay, 1 to A. So what is the delta system? Start this. What is delta system? Start this. Delta system. Tell me what? Tell me. System is what? The 3 steps. 1 to A to B, B to 2. So that is 1 to 2. Delta system is 1 to 2. A to B plus delta S B to 2 plus A to B plus B to what? A to A 1 to A to B plus delta S B to 2. How much it is? In value, copy the value. 0.51. Next is, tell me, minus 8.02 plus what is the next third one? Minus 0.49. How much it is? If you do this, 8, perfectly 8 joule, minus 1 is down. 8 joule per Kelvin, down. Keep save this. Delta surrounding, add this. Okay, next. Can I remove this? This part is over, so remove this, Now next is delta S surrounding. Delta surrounding, how try this? Delta surrounding, tell me, is minus, tell me, delta surrounding, next. Delta surrounding is what? Tell me. What? Q process by T surrounding. What is the Q process? Process contains 3 steps. What is this? And under constant pressure is delta H. So write this out. Q process. Write the first delta H by T surrounding. What is? I'm giving you. I will stop now. Delta H since constant pressure. Right? Since constant pressure. Right? Since constant pressure. Pressure process since constant pressure. Okay. What is this? So write this. So one by one, you do this. Delta H process minus first. You follow me, with me. Delta H what? Delta H. Shall we write this? Then you will understand. Delta H what is the first step? Tell me. Here is that 1, 2. Instead of entropy now, enthalpy, similar. Enthalpy, entropy divided by what? Delta H CPDT. Entropy CPDT by T. Entropy of phase transformation what? What is this? Delta HM. Entropy by temperature or freezing temperature, melting temperature. So this was the difference. So this is actually simpler than what is this? Delta H 1 to A plus delta H. Tell me. A to P process plus exactly, and instead of entropy is enthalpy. T surrounding how much? P surrounding how much? Tell me. Surrounding how much? That's right. It's over. Remove all this. This is box. This is important because this is your first part of calculation. Okay? Huh? So I think I don't have much time. Delta H one, what will be? Tell me NCPDT. N is one CPDT. CP lead liquid, right? CP lead liquid DT. What is the temperature? 590 to 600. Next is what? Tell me what is what? CP DT. And then it will be what? Minus enthalpy of melting because it is freezing. Minus delta HM. By okay, enthalpy minus freezing. Is it freezing? What is the enthalpy change? Freezing. Enthalpy, okay, enthalpy of this process it is freezing process. Then means minus enthalpy of melting. Plus next is tell me CP leads. What is this? Solid DT. What is the temperature? 600 to. Thank you so much. 600 to 5. This is good. When you do this thing, then very happy I am. 600 500. 100% correct. I am giving the result. What is the result? 6 minus is at the side. And what is 590? Write down the results quickly. Is minus. See minus is there. Write this 32.4. First one. Second one minus 80. Okay, you do this yourself with the limits 2 terms. 4810 minus 236 minus 58. What is the denominator? You do yourself. 590. What is the answer? Remove this. What is the answer? Answer is 4798 by 590. How much it is? 8.13 joule per Kelvin. Okay, surrounding system. What is delta S universe? Tell me delta S system, delta S surrounding. Your problem is over. Minus 8 plus 8.13 is 0. Plus. Note this plus 0.13 joule per Kelvin. So it is as expected for a spontaneous process. This is the answer. I gave you this answer. As expected, answer right. Answer first of all. As expected of a spontaneous process. You remove this unnecessary. These are unnecessary. Spontaneous. Thank you. I have to stop now. Thank you. What is your teacher? Sorry, I didn't know. Upstairs. How much? Mechanical. Okay, so I didn't tell. I forgot.